There's only high-frequency noise at your ADC input, no slow sine wave, no smooth, low-frequency signal. But in the microcontroller data, a clean, smooth wave suddenly appears. That's the real danger of aliasing. The error doesn't look like random noise. It looks like a plausible signal. It's not necessarily a bad sensor, a bad wire, or a firmware bug. It's sampling. A high-frequency component gets sampled in a way that makes it look like a low-frequency oscillation. The digital side does not get the full analog waveform. It only gets samples. And if those samples are taken too slowly, different analog signals can start to look the same. Here's a simple example. At the input, we have a 101 Hz sine wave. The ADC samples it at 100 samples per second. That already sounds broken. The signal frequency is higher than the sampling rate, and that's the trap. Each new sample lands at almost the same phase of the sine wave, just slightly shifted. The real signal oscillates 101 times per second, but in the samples, it looks like one slow cycle per second. So 101 Hz becomes a ghost signal at 1 Hz. Formally, this is called aliasing, or spectral folding. The alias frequency is the difference between the input frequency and the nearest multiple of the sampling rate. In this specific case, this is not a random error. It is a direct consequence of violating the condition for correct sampling. Now take a real example, a temperature sensor. The sensor signal changes slowly, but nearby, a switching power supply is running at hundreds of kilohertz. Its ripple can couple into the ADC input through the power rail, ground return, a long cable, or poor PCB layout. The microcontroller samples the sensor voltage, say 10 times per second. It cannot correctly represent that high-frequency noise. But if the noise is present at the ADC input during sampling, it will not magically disappear. In the samples, it can fold down into a slow component. Smooth changes suddenly appear on the graph. The engineer looks at it and thinks, the temperature is drifting, but the temperature is stable. What you are seeing is a ghost created by sampling. The Nyquist condition says that everything above half the sampling rate must be sufficiently attenuated before it reaches the ADC input. The key word is before. After sampling, it is already too late. The false low frequency is already in the data, and it looks like a real signal. That is why an anti-aliasing filter is placed in front of the ADC. Even a simple RC filter can help, if its cutoff frequency is chosen deliberately. Aliasing is dangerous because it does not look like an error. It looks like the truth. Subscribe for more practical breakdowns on DSP, ADCs, and real-world measurements.